Okay. Hello and welcome everyone to this talk titled The Minds of Kakadûm, Blindly Exploiting Load Balanced Services. Just to get the introductions out of the way, my name is Simon. I'm a senior security engineer for Google Cloud's vulnerability research team, in short CVR. I like to travel, read, and play with web apps, but I also do memory corruption. And I'm honored to co-present with Anthony today.
Yeah, so I'm Anthony. I'm also in the cloud vulnerability research team. I like reading and also hacking clouds.
So our collaborators are Juan Jose, who's a software developer for also CVR, and Ezequiel Pereira, who's also part of our team, but they're not on stage today. So with the introduction out of the way, I want to give you a brief overview of what to expect of this talk, and we'll describe the problem that we face when we try to exploit a load balance service through memory corruption. And then we'll introduce Kakadu, which is a JPEG 2000 library, hence the name, The Minds of Kakadûm. And then we'll get into some vulnerabilities and how we managed to overcome the obstacles that we faced, and then we'll end with a demo. So what problems could you face? So let's assume you have some kind of load balance service, some kind of cloud service, some kind of microservice, some kind of backend, and you have no real overview of how the application works internally. So you throw the usual vulnerabilities at it, like path traversal, SQL injections, command injections, but nothing really works. But you can identify usage of a memory unsafe language, like any image processing library, things like that. But this attack path is often discarded because there's a lack of knowledge of the environment that you're trying to exploit. Like you don't know what allocator is being used in the backend, so you can't really debug any heap spray failures. You don't know what OS and architecture are used in the backend, so you don't really know how to prepare shellcode. And then last but not least, even though you may be able to identify the library, it might be compiled with a different version, custom flags, or it might be just compiled into the main binary. So you don't really have the binary and offsets to RobChain gadgets or to any data-only exploits. And as a result, the whole treasure trove of possible targets is often ignored. And of course, the second problem with memory corruption is that oftentimes these exploits have a two-stage approach. So with the first bug, you'll leak some kind of pointer to break ASLR, and then with the second stage, you'll attempt to overflow memory and then deploy a RobChain. But in a load balance context, if you have this two-stage approach, you have no guarantee of hitting the same worker again. So depending on the reliability of the service, you might just bring down production and you have a very unreliable exploit. So there are some techniques like one-shot exploits or partial pointer overwrites, but these require more specialized gadgets. And today we'll introduce more specialized gadgets, so it's another tool in the toolbox. So yeah, what we did for this was reusing application logic to only trigger memory corruption if certain conditions are met, so that we can be sure we're hitting the right worker with the right ASLR offsets, which we're expecting. And we call this conditional corruption. So I want to introduce Kakadu and some basics on the JPEG 2000 file format so that we can move on to the interesting part, which are the vulnerabilities. So again, Kakadu, JPEG 2000 processor, named after a national park in Australia. It's closed source, but customers get access to the source code. And the demo binaries are freely available, so you can just download them and reverse engineer them. You can also just purchase the standard, which, as we'll see, has some interesting information. And to quote from a Cisco Talos report, the software is used by many high-profile companies in the handling of JPEG 2000 images, including Apple. Beware, though, that this report is from 2017, so that might have changed. And this library was also used by a Google service, so the exploit we're describing today was exploiting a production service from the perspective of an external attacker. That's why some of the details of the exploit might be a bit more abstract, because we can't include all the details. So let's get into the 101 of the file structure. The entire file is made up of length type value boxes. And on the right-hand side, you can see the minimum layout for a JPEG 2000 file. The first box is a JPEG 2000 signature box, so you just have the length of the box, which is 4, because there's just 4 bytes of signature, and then you have the type, and then the hard-coded signature, and then you have some more header boxes that provide some of the meta information to the parser, like what is the image size, what is the resolution, which camera was this image taken with. And then the most important box is the code stream box, which contains another file format within it that contains the actual image data, the actual compressed data. So here we can just see again the layout of such a box. We have the LBox field, which is 4 bytes for the length. We have the T-box, which is just a hard-coded value for depending on the type. And then we have the XL box, which is an optional field that we don't need to get into right now. And then we have the box data. So the parser is very simple. It just reads however many bytes are in the LBox field, figures out which handler to call for this box, and then just parses the box. And it's also important to note that boxes can contain sub-boxes. So the actual important things are the code stream box, and it's also divided into a type length value structure where one marker is called a marker. And at the bottom, we can see the structure of a simple comment structure. The reason I chose this comment structure of the marker to show here is because, for one, it's very simple just to understand the structure of what we're talking about. And later on, we'll actually need the comment marker for quite a few things. So we can see the first 2 bytes are the type field, the comment, and then we see the length, which can be a maximum of 65 kilobytes due to the 2-byte size of the length field. And then rcom is a comment-specific marker. It just indicates if the comment data is in text or binary, and the remaining bytes are simply the comment itself. So the Kakadu parser also just sees how many bytes there are to the comment, and in this case, it just jumps over the comment data because it doesn't use it for anything. Another very important marker that we can't skip over is the size segment marker, which provides information about the size of the output image, so the raw decoded image, how large it is. And for that, we have the highlighted X size and the Y size field, so that's a simple XY coordinate. And then we have the XT and YT size, and these are the sizes of tiles within the output image. So the output image is decoded in equally sized tiles, and we can see the structure here where you tell how many, what is the size of one tile, and then it's divided. And then the coordinates of a single tile can be calculated just from the index alone of a tile. So what the parser will do, it will go through all of the different tile markers, and we'll get into those on the next slides, figures out what the offset is, and then decodes the data, and then writes it in the correct position into the output image. So here we can see, and this is the last marker that I have to get into, and then we can get to the vulnerabilities. We see the start of tile marker, which has the normal length field, and then has the tile index, which Kakadu then uses to calculate the position of the decoded data. And then it has a 4-byte field, which contains the length of the decoded raw data that comes after, because the decoded data could be longer than 65 kilobytes. So then we see the counterpart, the SOD marker, which doesn't have a length field because this contains data that might be longer than 65 kilobytes. So typically, you just have a stream of these SOT markers with their index. How long is the decompressed data? The data decompresses it and then moves on. So with that one-on-one knowledge out of the way, I can hand it over to Anthony to discuss the vulnerabilities that we found.
Yeah, so thank you, Simon. I'll be talking about 2 vulnerabilities that we found, info leak and then memory corruption, and then how we exploited them. So the first one is an arbitrary file read. And for this, we have to go to the JPEG 2000 standard. So this is not a vuln just in Kakadu, but it's also just directly written in the standard as vulnerable. And this is part 2 of the standard, so you have to pay a little extra. So we look from the standard, there's a diagram that shows this feature of JPEG 2000 called fragmentation. And what this lets you do is take one large JPEG 2000 file, split it up into multiple fragments, and then distribute those fragments either throughout memory or maybe from local files, or even split them out and put them on different servers on the internet. And if we see here, there at the top is the actual bytes of the image, and at the end of the image, you put a data reference table and a fragment table. The data references are simply a list of pointers to either local files or URIs that it could be like HTTP or FTP servers. And then the fragment table is basically a sequence of all of the different fragments that, if you read them one at a time, it reconstructs the code stream of the image. And so we see here that first fragment, the yellow fragment, is some index into the actual file, the image file itself. And these can be an arbitrary offset, an arbitrary length. Then the second fragment, the green one, that's loaded from some local file, the data reference. And again, this can be at any index in the file and any length. And then the blue one, again, is just a different file. If we go down further, there's a red one that references some HTTP URL. We found in our testing that like Kakadu doesn't implement this HTTP mechanism, but it does implement the local file mechanism. So we would like to use that to read arbitrary files. And the way that we can maybe do this is basically we control bytes of the code stream that is used to construct the image. And those bytes are controlled by local file contents at arbitrary offsets. We need some oracle, though, to be able to like extract the data that we're leaking. And here are the assumptions we make about our target service. So assume it's a very basic image conversion service, it just takes in one JPEG 2000 file, and it outputs raw pixel data, just an array of RGB. The reason we made this assumption is, one, it was very similar to the service we were exploiting in production, but two, it's the simplest version of this. So like we're stripping all metadata, we're just assuming all we get is RGBs. If it works in that, then we can probably extend the exploit to anything else. So here's an example oracle. This is the first one that we tried. Like Simon said, there's a marker in JPEG 2000 called the size marker, and this controls the width and the height of the image. So what we can do is, for the bottom byte of the width, we can say that that is a fragment that references 1 byte from a local file. And then we do the same thing for the height. Then when this is rendered, the actual output image, it'll be all blank, but the dimensions of the image will be the leaked bytes. And so using this mechanism, we can leak 2 bytes per request by just running this through and then looking at how tall the image was and how wide it was. So that's nice, but 2 bytes per request isn't very much. So we would ideally like to leak more. You might think, okay, well, somewhere in this code stream, there's like a section of data that's just RGB, right? Like there's going to be a section for the pixels. Can't we just reference a local file there and then just leak data directly in the RGB values? The unfortunate answer is no, and we don't have time to get into why, but basically there's some low-level details of JPEG 2000 that make this basically impossible, some like variable length encoding and a bunch of math. So we had to find another way. And for this, we started dreaming of weird machines that we could make. So I'll ask a quick question. I'll pose this to you, is let's say we have these bytes that are all like various comment markers of different lengths. And say we have like one fragment byte that is in the length of the first comment marker. So the question is, like, how many comment markers do we see in this image? One interpretation of that is 3 comments. If the byte that we leaked was a 4, then the first comment would be correctly identified as 4 bytes long, 4 A's. Then the next comment is 2 bytes, and then the next comment is 6 bytes. But what if the byte that we leaked was 12? Then the first comment keeps reading past the end of the intended array and consumes the entire next comment marker. So in this image, if we leaked byte 12, there's only 2 comments. And we basically jumped over a whole marker in the image format. So this jumping mechanism is something that we used in order to basically start performing searches and like build some sort of like conditional logic mechanism in the format itself. And so I'll show you what this looked like. So here we have 3 example bytes that, the byte that we leak is unpredictable, but let's try a few examples and see what happens. At the beginning, we have one comment marker whose top bits of the length are the fragment, and those come from the leaked byte. And then we have like some padding of 16 A's. After that comment, we have a sequence of 256 like jump table entries, which each entry is made up of a start of data, which outputs a particular color, and then a comment that consumes all of the rest of the jump table. And so we have an animation to show what this looks like. So let's say that we were to leak the byte 0. In that case, the comment is just 16 A's. You output start of data that is a 0, which is just black, and then the next comment marker will consume all of the rest of the data because it is quite long. Then maybe say we leak byte 1 instead. In that scenario, we jump over the first start of data, and instead now we're outputting a value of 1 for the pixel, and again the comment marker just consumes all the rest of our jump table entries. And then just to show you, you can probably see what happens, but when it's FF as our leaked byte, we jump over the whole table down to the very end and output just a white pixel. So with this mechanism, we can basically repeat this over and over. And we also, just as a different way to visualize it, we showed it in like pseudocode basic. So each line of this basic program corresponds to a marker in JPEG 2000. And you can see we have like this goto that's dependent on the leaked data, and then we're printing different colors using the start of data tiles, and then the comment marker with like a large length lets us jump to the end. So what does this look like in practice? We'll have like a pretty big image with all of these jump tables, and you can see in the image there's a lot of A's because we have to pad everything to multiples of 256. But we send this to our converter service, and out comes this beautiful picture that shows you in like the pixel data what the leaked bytes are. So in this case, we're leaking proc_self_exe of one of the Kakadu demo binaries. Using this technique, we can leak 20 kilobytes of data per request. Some files you might want to leak is like proc_self_env, exe, maps, mem. We ended up using a few of these in our exploit, particularly proc_self_maps, so that we can just break ASLR. So now we come to the second vulnerability. This was an integer overflow. So in our target service, we were using Kakadu as a library. And when used as a library, the caller is responsible for calculating and allocating the memory region that holds pixel data. The memory region has to be big enough to hold all of the pixels. So it's width times height times like the number of colors big. And Kakadu represents these values as 64-bit integers. And so you can see some code from our target service where we multiply those things together using safe multiply functions to make sure there's no integer overflows. But you may have noticed in the actual image format, these are tracked as 32-bit values, not 64-bit values. So internally, Kakadu represents all of these integers as signed 32-bit integers. Now, when Kakadu is writing data out to this buffer, it writes pixels out one tile at a time and one row at a time within a tile. To calculate where to write the second row, it advances the pointer by width times the number of colors, where both of these are signed 32-bit ints. And then it doesn't do any overflow checks, which means we can overflow that calculation and advance the pointer backwards and start writing data like before our image buffer. It'll look something like this. So the first row of pixels gets correctly written into the image buffer, but then the second row of pixels gets written at this large negative offset. So we just overwrite random data on the heap. Then if, let's say there's multiple tiles, the next tile gets correctly written, but then the second row of pixels goes onto the heap. So at this point, we can write backwards on the heap by a very large but known distance. It's like around 4 gigabytes in order to trigger the overflow. And the nice thing about that is that tcmalloc, which was the allocator used in our target service, has very specific behavior for large allocations. So if the heap doesn't have enough space to hold your large allocation, tcmalloc will just expand the heap by exactly that amount and then return a pointer to the previous top of the heap. And so what this looks like, we leaked proc_self_maps before and after the allocation, and you can see that the top of the heap before the allocation was this 04000 address, and then after, the address at the top of the heap is this 24000 because we requested an allocation of like 2 million bytes or whatever. And then the returned pointer is that 400 value that was the previous top of the heap. So if we were to leak proc_self_maps before the allocation, we'll know, because our data is so big, we'll know exactly where it's allocated. So next, our heap spray primitive. For this, we went back to the standard and looked through all of the different markers that allocated like arrays of data. And there's a pretty nice one that allocates this thing called a super box, which a super box is just a thing that holds more boxes. And in particular, this composition layer extension box has several integers where you just tweak them and it allocates like large arrays of objects. So we picked one of these, specifically the JX track source, which is a 696 byte object that we could allocate like hundreds of thousands of times, like create many megabytes of just this object on the heap. And the destructor of JX track source calls another destructor, which calls this close function. And within the close function, we found a write what where primitive. So assuming we control the whole object, we can set all of the values to pass some of these like if statements. And eventually, if you look at the bottom line of this decompilation, there's this write to parent box, writing box position in. And the box position is this 64-bit int that we control. Parent box is a pointer that we control. So if we get to the destructor of this method, then we can write arbitrary data, arbitrary address. Also, because it's like a huge array, and we can overwrite like quite a bit of data on the heap, we can do this multiple times. So we can set up like multiple 64-bit writes, and that's ultimately what we used for like a data-only attack against our target service. So at this point, we got into what we called exploit reliability engineering. So like we're testing in prod, and we would really like to not take down production services, even though like they're resilient and you could probably kill half of them and it would still work, but we'd still like to not do that. So there were a few problems we identified that we will have to overcome if we want to increase our reliability. The first one, we might leak the address layout in one request, and then our next request, it is very likely that we hit a completely different worker. Like there's hundreds to thousands of different workers. It's basically guaranteed that we won't hit the worker that we want on the first try. In order to get around this problem, we used the arbitrary file read to read from proc_self mem at an address that we knew was mapped, at least in one worker. And what Kakadu does internally is it will open this file and then seek to the offset that we tell it to. And proc_self mem is this special file. If you seek to an address that is unmapped, then the seek returns an error. And so this error like populated up the stack, and Kakadu basically stops processing the function if the seek fails. So in the first request, we leak an address. Then in our exploit request, we do this seek, and if our address is wrong, then we just error out and we can try again. We don't crash anything. The next thing that can happen is maybe the heap might change, right? Like we need to know the address of our image buffer, and if we're wrong about that, then we could cause some problems. So the way we get around this is we do another file read to proc_self maps in the exploit payload. We know what byte should be at the top address of the heap, and we know where it is because we already leaked this file once. So we just basically put in another comment marker conditional jump thing, and if the byte is what we expect, we keep going and do the rest of the exploit. If it's not what we expect, we do like an invalid marker, and then Kakadu bails out early. Then the last challenge is the heap spray. So JX track source, we've got this huge array. It's this really nice primitive, but it'll be allocated at some unknown offset. And it's 696 bytes long, so we have like a 1 in 696 chance. And if we guess wrong, we crash. So we would like to not do that. If only we had some sort of like weird machine that could deliver precisely the right exploit payload by like searching for the offset. So we reused our like same conditional logic from before, but this time we instead of having 256 bytes for each like leaked byte, we have 696 exploit payloads all encoded in the same image, and then we scan the heap 696 times, looking for one of the bytes in the V table of JX track source. Then as soon as we find that byte, we output the exploit payload and then get code execution. So what this looks like, let's say that E0 is in the V table. If that gets put in the comment marker, we skip over all of the exploit payloads that are wrong, deliver the exploit that is coded for that offset, and then again, consume the trailing comments and stuff. And so with that mechanism, we had 100% reliable code execution, and I'll pass it over to Simon for a demo.
Okay, Thank you, Anthony. So we'll close this off with a demo of what the exploit might have looked like. So we're going to run this, and we're going to target something, and then we'll send two images. The first is to leak proc.self exe from the target service. So we've already previously leaked that in a previous step in order to prepare the final exploit steps. But in this case, we want to make sure that the binary is still the same one as the one we were expecting, just to make sure we're not crashing on accident. And the second is, of course, proc.self maps, because we need to break ASLR. Oh, that should not have happened. Sorry. So now we confirmed that proc.self exe is still what it's supposed to look like, and we're decoding the image, and we can see proc.self maps was leaked, and now we're waiting for a reverse shell. And there it is. So to conclude the talk, we reused application logic to only trigger our bugs when we wanted them to, when we arrived at a desired worker. And we used a similar technique with CV 2023-29077, which was used to achieve remote code execution against ClamAV. And that bug won a Pony Award in 2023. And we used an out-of-bounds read and the value out of an out-of-bounds read to influence the application logic. And that way we could side channel the value of it, but we could also decide if we would want to continue with our current exploit attempt or not. So again, we overcame the issues of load balancing with more specialized gadgets. So of course, this will not work for every single bug there is, but it's another tool in the toolbox. And we're looking forward to seeing more techniques for fingerprinting libraries remotely, and also for remotely identifying binaries. So in this case, we used an arbitrary file read, but you could also use, say, out-of-bounds reads to leak pointers to standard libraries or fingerprint standard libraries another way. So when we will release the slides, we'll release an extended version with some more ideas for techniques for fingerprinting. But since we opted for the short talk, we left that out for today. And so I think we might have time for one or two questions, in case there are any.
Hi, thank you. Thank you for the talk, very good. I have two questions. The first one, are you aware, it looked like this library is very powerful for doing this kind of thing. Are you aware of other libraries that could give this kind of nice primitives remotely? And the second question is, I missed if tcmalloc was important in the exploits, or if it's because you can't know in advance remotely, so just wanted, thank you.
So for the first, there's not many JPEG 2000 implementations. Most of them do not implement the file read primitives. So Kakadu does, but it is part of the standard. So we've worked with the people to get the standard changed. So it's definitely possible that custom implementations are still out there that are vulnerable. For the second question, why tcmalloc was important to the exploit was because the image that we allocated in the end was really, really large, because we had to overflow the integer with it. It would always be placed at the end of the heap, so it would always be prepended to the heap. And since we could use the bug to write backwards, that's why it was important. So this might have worked differently with other allocators.
Okay, thank you.
Okay, so with that, we'd also like to mention that we're hiring. So if you have any more questions or you're interested, feel free to approach us anytime offline, and thank you very much.